Okay, welcome to the second video. We got chapter 4, section 2. It's going to be all about the unit circle. So a couple things of what you guys are going to be learning in this section. You're going to learn how to identify a unit circle and describe its relationship to real numbers. Evaluate trigonometric functions using the unit circle. Use domain and period to evaluate sine and cosine functions. And use a calculator to evaluate the trigonometric functions. So what you have down here is the unit circle. We're not going to go through how to derive each of these coordinates here. We did that back in Algebra 2, but it does come from the fact that if you were to drop a vertical from each of these points, it forms a special right triangle, in this case a 30, 60, 90, and these coordinates come from the ratios of a 30, 60, 90. For example, this hypotenuse is 1, therefore the short leg is half the length of the hypotenuse, and the long leg is root 3 times as long as the hypotenuse. So we get the coordinates root 3 over 2, comma 1/2. That's what we see here. And you can do the same for each of these points around the unit circle, alternating between a 30, 60, 90 and a 45, 45, 90. But it's up to you to know all the coordinates on the unit circle in order to answer these questions quickly and accurately. Okay, so what are trigonometric functions? There are two historical perspectives of trigonometry, and they incorporate different methods for introducing the trigonometric functions. The first introduction to these functions is based on the unit circle that we referred to earlier. And the equation of the unit circle is just x squared plus y squared equals 1. That's because the unit circle is centered at the origin of the xy plane, 0, 0, and it has a radius of 1. And so again, here's our unit circle. Note, if you have to reference, it's on the second page and the third page. So let's start to introduce the trigonometric functions in reference to the unit circle. So the 6 trigonometric functions that we're going to be working with are sine, and I'm going to write sine of theta. Sine is spelled, here I'll spell them out for you, S-I-N-E, cosine, C-O-S-I-N-E, abbreviated C-O-S for cosine, tangent, T-A-N-G-E-N-T, abbreviated T-A-N, and their reciprocals, so cosecant, abbreviated CSC, secant, abbreviated SEC, and cotangent, abbreviated COT. Okay? Now, these functions are defined on the unit circle to be in this way. Sine of theta is defined to be the y-coordinate of a point on the unit circle. Cosine of theta is defined to be the x-coordinate on the unit circle. And tangent of theta is defined to be the y-coordinate divided by the x-coordinate on the unit circle. These three are just the reciprocal of sine, cosine, and tangent. So cosecant is going to be the reciprocal of y, which is 1 over y. Secant is the reciprocal of x, so 1 over x. And cotangent is the reciprocal of y over x, or x over y. So let's evaluate these 6 trigonometric functions at each of these real numbers. Let's start with pi over 6 radians. So what would sine of theta be in this case? Well, let's look back to our unit circle. And as you can see here, pi over 6 has an x-coordinate of root 3 over 2 and a y-coordinate of 1/2. So, sine of theta being the y-coordinate, sine of theta of pi over 6 is going to be 1/2. That's the y-coordinate of a radian measure of pi over 6. Cosine of theta is the x-coordinate, and as we saw earlier, that's going to be root 3 over 2. Tangent is the y-coordinate divided by the x-coordinate. So in this case, that's going to be 1/2 divided by root 3 over 2. And we can simplify this a little bit. When you have 1/2 divided by root 3 over 2, the denominators are equal, and when you have two fractions dividing one another where the denominators are equal, you can actually just divide out those denominators. They cancel. So you're left with the 1 over root 3. But, of course, we have to rationalize that. So we're going to multiply this by root 3 over root 3, and we find that tangent of theta will be root 3 over 3, because the denominator is root 3 times root 3, which is root 9, and the square root of 9 is 3. Then the other three functions, again, they're just the reciprocals of the three that we just found. So cosecant of theta is going to be 2 over 1, which is just 2. Oops, you can't see that. Secant of theta is going to be 2 over root 3, which means we have to rationalize that by multiplying by root 3 over root 3. So we find secant of theta is 2 root 3 over 3. And cotangent of theta is the reciprocal of tangent. And so that's going to be, or it's x divided by y. So that's going to be root 3 over 2 divided by 1 over 2. And again, those 2's divide out, so we get root 3 over 1, which is equal to root 3. So I'm not going to go over these three more examples. You can try those on your own and in class next time. So moving right along, we have this example down here, determining the domain and range of sine and cosine. Okay, so what that means is the domain is all the possible inputs into sine. Now let's go back to the unit circle for a second. Your input into sine is actually an angle. And from our last example, our last lesson, we saw we can have positive angles, negative angles, angles over 360 degrees, and all of them, all they refer to is just some position around this circle. Like 120 degrees is here. Negative 120 degrees would just be in the opposite direction, so down here, even though it doesn't say negative 120, that's coterminal to 240. And so I can actually put in any angle measure I want into sine, because it'll just allow me to land somewhere on this unit circle, which means my output is just going to be whatever y-coordinate I have. Similarly, cosine is just the x-coordinate of whatever I'm at. And so I can, once again, put in any positive angle, any negative angle, a zero angle, and I would end up somewhere around this unit circle, which means I would have an output for x. So the domain for sine and cosine is all real numbers for both of them. So our domain is all real numbers. The range now. Let's talk about just sine first. Go back to our unit circle. Our range is all the possible outputs. In the case of sine, that's all the possible y values on the unit circle. So what's the smallest y value? Well, how far down can we go? The farthest down we can go is this y value of negative 1. Similarly, the farthest up we can go is positive 1. And we can go actually all the way around the circle and get any number in between. So the range for sine is going to be negative 1 to 1. So we're going to say the range is from negative 1 to 1, and we're going to use brackets because we want to actually include the negative 1 in the 1. Now for cosine, it's very similar. The cosine outputs, though, are the x-coordinates, so we got to look left right now. But notice the farthest left we can go for our x-coordinates is negative 1. And the farthest right we can go for our x-coordinates is positive 1. And if we go around the circle, we can get all the x-coordinates in between negative 1 and 1 as well. So the range for cosine also happens to be negative 1 to 1. So cosine and sine, they actually have the same domain and range. The domain for each of them is all real numbers, and the range for each of them is from negative 1 to 1, including negative 1 and 1. Example 4, we have to determine whether each trigonometric function is even, odd, or neither. Okay, we have to recall what even, odd, or neither means. If we have our function f of x, let's say, I'm just going to do a quick polynomial to remind us what it is. If our polynomial is, say, I don't know, 3x cubed minus x. Is this odd or even? Or neither? What we have to do is check f of negative x, right? So f of negative x is going to be 3 times negative x cubed minus negative x. Simplifying this, if I cube a negative, that means negative times negative times negative, which is going to be negative. So I get negative 3x cubed, and if I have minus negative x, that becomes positive x. So let's take a look at the signs. 3x cubed was originally positive, now it's negative. X was originally negative, now it's positive. Since all of the signs changed, this is going to be an odd function. Now you might say, well, how do I do that with sine? Right? If my function f of x is sine of x, what would f of negative x be? I don't have a idea, like I can't just square x or square the negative x to get an answer here. So whenever we're in this position, we can do a couple test points. Let's choose a positive value of x, and let's choose a negative value of x and compare their outputs. So I'm going to use angles that are on the unit circle, like I'm going to say 30 degrees and negative 30 degrees. So what is f of 30 degrees in this case? That's going to be sine of 30 degrees. And what's sine of 30 degrees? Let's go back to our unit circle and figure it out. So our unit circle says 30 degrees is here, and sine is our y-coordinate. Our y-coordinate is 1/2. Okay, so that means sine of 30 degrees is 1/2. So let's now evaluate f of negative 30 degrees. That is sine of negative 30 degrees. Similarly, let's go back to our unit circle. Now 30 degrees was up to here, right, in the positive direction. So negative 30 degrees is going to be right here, same amount, just in the negative direction. And if you look at the y-coordinate here, it's negative 1/2. So, because the output, the sign changed from positive to negative, sine is going to be an odd function. So sine of x is odd. And what that means is that if you have sine of negative x, that's equal to negative sine of x, okay? You definitely want that down for sure. And you want to know that sine is odd. So sine is odd, and because it's odd, it has this property. Sine of negative x equals negative sine of x. Let's do the same thing for cosine. Let's say our f of x now is cosine of x. What would f of negative x be? Well, just like with sine, we're not really sure how to really look at that. No shortcuts, no squaring going on. So let's go back to the unit circle. Now I'm not going to turn back again. You can turn back and follow along. Let's evaluate what f of 30 degrees is. Well, that's going to be cosine of 30 degrees. And if you see on your unit circle, cosine of 30 degrees is the x-coordinate at 30 degrees, which is root 3 over 2. F of negative 30 degrees, which is the same spot as 330 degrees, you'll also get root 3 over 2, the same thing. And when you have the same sign, it signifies that the function is even. So cosine of x is even. It's an even function. Which means if I have cosine of negative x, that's actually just equal to cosine of x. It changes back to normal. As if that negative wasn't there, you'd get the same answer. Okay, moving right along. Example 5, we want to use a calculator to approximate these two values. So, first question for you, are these values in radians or degrees? Well, there's no degree symbol. And whenever there's no degree symbol, we have to assume these angles are in radians. So in our calculators, let's hit mode and double check. You see over here where it says radian? Your calculator might be in degree mode. It might be like looking like this, and if that's the case, you're going to get the wrong answer. You have to change it to radian mode. Once you do so, you can go back to the calculator's home screen and just do sine of 2 pi, and your pi key is actually right here, over 3. Close your parentheses, hit enter, and we find that this is approximately 0.866. So this one is here is 0.866. Now cotangent, you may be wondering, oh, I don't have a cotangent button. I have a tangent button, We have to remember cotangent's just the reciprocal of tangent, right? So if I find tangent, I take the reciprocal of it to find cotangent. And how to do that on the calculator is you just do 1 divided by tangent. That will be equivalent to doing cotangent. 1 divided by tangent, and then we type in 1.5. And then hit enter. Because we're still in radian mode, and this 1.5 is not degrees. There's no degree symbol here. So you're still working in radians. And we find that this is going to be approximately 0.07. Or 0.071 if we're going to 3 decimal places. Okay, that's all for today. So we're going to stop here, and we're going to work on these problems on the next few pages in the next class. All right, see you later.